Okay guys, in this last video we're going to take a look at using continuous growth models to represent, say, population growth or decay, and really to kind of also compare populations that are growing at different rates or maybe have different initial quantities. And so one thing that I want to point out here is that when we're looking at population growth or decay, we often like to use our continuous growth models in order to do this. And so recall that our continuous growth or decay models they come in this package right here. An amount at a given time t is always equal to some initial amount times e to the rate times time, or another way to look at this is we can say y equals our initial amount times e to the rate times x, or x is our time here and y is our amount at that given time. So we're going to be using these models in order to describe these populations in this particular instance. And the really important thing is that we can actually just find a model for these. So I'm really rubbish at writing with this thing, so I'm going to type it. But what I want to make sure that you write down here is this. Whenever we want to write a continuous growth model, we must know both the initial amount and the rate in order to write a model. Okay. So if that's the case, then really the name of the game here is, when we're going to be looking at these models, determine what the initial amount and the rate both are. So let's take a look at this example that I have here. It says the population of the United States in the year 2000 was 0.282 billion people. In the year 2003, the population was 0.290 billion people. So you can see that in the course of 3 years, the population of the U.S. grew. It says model this with a continuous growth equation of the form u of t equals ae to the rt, where t equals 0 represents the year 2000. Excuse me. So in this particular case, what I want you to recognize first of all is this u of t is kind of saying that this is the population of the United States at a given time, and t is our time here. So our a is going to be representative of our initial population value, and r is going to be representative of our rate here. And we need to know these two things in order to write this model. So what is it that we already know? Well, first things first, t equals 0 represents the year 2000. So in terms of what our initial amount is, I can already tell you that if this is the year 2000, sorry, let me move this out of the way here, and that's time 0, okay, then this right here is our initial amount. Because this is time 0, we already know then that this is our initial amount. So the only thing we don't know is the rate, but at the same time we were given a time and a population ordered pair or data point here. And so just like in our last problem, that's going to allow us to work backwards in order to solve for that rate there. So let's go ahead and take a look at part A here. And what I want to do is just go ahead and set up what we know. We say u of t, or the population of the United States at a given time t, is equal to the initial population, 0.282, e to the, and we're just going to leave this as rt. We're not going to do bx. We're going to do rt to keep in line with this model in the form that it was given to us here. But what I know is, I suppose if we're going to do our due diligence here, let's go ahead and put in a table over here. We say at a time, we have some population in the United States at that time. We know that at year 0 it's 0.282, but at the same time we were given another data point here saying that in 2003 it was 0.290. So what we can do is we can actually plug this data value into this equation for both our population and time, and what that's going to do is it's going to allow us to work backwards to solve for the rate, and that's precisely what I want to be able to do here. And so let's go ahead and say that we know that the population, let me try that again here, 0.290, be 0.290 billion if we had started with 0.282 billion, and we say this is e to the rate times 3. In other words, 3 years later, we know the population of 0.282 became 0.290. So let's start with solving for r by isolating the base e here. And so I'm going to go ahead and do this. I'm going to divide both sides by the 0.282, 0.282. So we get 0.290 over 0.282. And this is equal to e to the 3r is how I'm going to write this. And so because we have isolated our base here, I'm going to go ahead and wrap both sides up then, and we're going to take the natural log of both sides in order to use our inverse property And we say that then the natural log of 0.290 over 0.282 is equal to 3r, where now all we have to do is just divide this by 3, and what that does is it kind of just isolates r. And so I won't be lazy here. We say divided by 3, divided by 3. I may need to pop over and use a new canvas here, but we can fit this in right here. ln of 0.290 over 0.282, and all of this is being divided by 3. So this is our precise rate of growth of the population of the United States in this particular instance. So let's go ahead and get a decimal value for this, and we say the ln of 0.290 divided by 0.282, end parenthesis, all of this divided by 3. We get this rate right here, which is actually not too incredibly small. We're going to go up to the first 4 non-zero decimal places. So we have 0.009325. So we have rate is 0.009325, and I'm going to throw a box around this. And so I'm also going to scroll down and say, well, then for part A, our job was to write a model. Okay, we can actually go ahead and write our model now, and maybe I don't need to put that down there. I can just put it up here. We say that our model then would be the United States population at any given time is equal to the 0.282 billion that it started with, e to the, and we have growth in this particular instance, so I'm going to write positive 0.009325 times the time. And this right here is what all we were trying to do for part A, is just write a model that describes how this population is changing over time. It's just that we had to go solve for the rate first in order to get this model complete. So now we have our model here. Part B says Mexico's population is modeled by Mexico's population as a function of time equals 0.097 e to the 0.012 t. So my question here is, which country, the United States or Mexico, has a population that is growing at a faster pace? And so when we talk about faster pace, we really are referring to the rate. And so we're going to say the rate of the USA. In this particular case, we just solved for it. And when you look at this as a percentage, this would be moving our decimal twice back to the right, 0.9325. And so what I can say is the rate of growth is 0.9325% in the United States. Now, when you look at the rate of growth of Mexico, okay, you look at their model and the rates right here, it's 0.012. In other words, if we move that decimal back twice to the right, what we end up with is a 1.2% rate. And so this one's pretty simple to make up our minds on here. It looks like the rate of growth of Mexico's population is higher than the rate of growth of the United States population here. And so when it says explain your answer citing specific information here, I'm actually going to make sure that I get some really nice text here. But we're going to say the rate of Mexico's population is higher than that of the United States population, since it is, I don't want to write on top of that, since it has a greater rate. Okay, sorry that I couldn't fit all that in there, but I would actually, if I was writing this by hand, I would cite specific information here. And so I would say Mexico's rate of population is 1.2%, whereas the United States population is 0.9325%. So Mexico's population is growing at a faster rate than the United States population here. So for this last part here, it's kind of a two-parter. It says, if you believe that the U.S. is growing faster than a rate of Mexico, then find the population of the United States in the year 2150. And so what I can tell you is we're not going to do number one, and the reason why is just because we just determined that the United States population is not growing as fast as Mexico's population. So for part two here, it says, if you believe that Mexico is growing at a faster rate than the United States, then find the year in which Mexico's population will overtake that of the United States. And so what I want to kind of do is I want to kind of represent this graphically. And what I'm going to say is, if I were to represent this graphically, we would have some time, okay, on our x-axis, we would have the population of both countries. And so what I notice is, at least if I go back up here, the initial population of the United States was 0.282 billion, whereas the initial population of Mexico is 0.097 billion. So Mexico is starting with a lower initial population. And what that means, I suppose, is our y-intercept for the United States is going to be higher, and it's going to be growing like this here. But Mexico, and I'll put U of t here. But Mexico is going to be starting with a lower initial population, but at the same time it's going to be growing faster. And so there's going to be this time, okay, at which they both have the same population at the same exact time. And what we're trying to really do is figure out what is this time at which these two populations are exactly the same. And so what we're going to do is we're going to set the population of Mexico at a given time equal to the population of the United States at a given time and say, what is t? And so it's kind of like we're going to have to solve a system here. And so what we're going to do for part 2 here is we're going to equate the populations and solve for time. Okay? So in this particular case, I'm going to say let's set the United States population equal to Mexico's population. And again, I'm going to borrow from a new canvas here. I'm going to say United States population is equal to Mexico's population. And so we're going to set these two models equal to each other. And that is to say that, you know, we have this model that we wrote here for United States population, and we have this model here for Mexico's population. If U of t equals M of t, then we can set these two algebraic expressions equal to one another. And so we have the United States population 0.282 e to the, let's go back and look here. We have 0.009325. So we have 0.009325 t. And we're going to set this equal to Mexico's population model, which was 0.097 e. So we have 0.097 e to the, and in this case, what was it, 1.2%? Yeah, so 0.012. So 0.012 t. And so what we're going to do is we're going to solve for time. Now, here's what I'm going to do. I'm going to give you some advice, and that is to say that when you have something like this is hardly a one-to-one property situation. I can't say, you know, e to the x equals e to the y if and only if x equals y. And the reason why is because I have a lot more stuff here than just e to the power of something on the right and e to the power of something on the left. And so what I'm going to ask you to do is, well, I suppose we are going to divide both sides by the e to the power of the smaller rate. And so what that looks like in practice is simply this. Okay, I noticed that the United States had the smaller rate, and so what I'm going to do is, let me get my pen tool out here. We're going to divide both sides by e to the 0.009325 t. And this is going to happen on both sides. So e to the 0.00932 t. And what that's going to end up doing is it's going to end up getting the e's off of this left-hand side here. And so what we're ending up with is 0.282 on the left, and this is equal to 0.097 e to the power of what? Now here's the curious part. I'm going to say e to the power of 0.012 t minus 0.009325 t. And the reason why is because when we divide two things that have the same basis, like b to the m divided by b to the n, the rule is that we keep the same base and we subtract their exponents. So in essence, what that's going to do for us, and let me get out my calculator here because I need to subtract these, 0.012 t minus 0.009325 t gives us this new decimal here in our exponent. 0.282 equals 0.097. This is e to the, let's go look here, 0.002675. 0.002675 t. And so in other words, now when we divided our e to the power of something by e to the power of something, we were really dividing two things with the same bases, which allowed us to subtract our exponents and write this as just a single base of e. And really the important thing there is just we're solving an exponential equation, which involves getting the base by itself. So we had started off with two population models equal to each other, but we had bases on either side. If we're going to solve for the unknown and the exponent, we got to get the base by itself. So let's go ahead and do that now that we have just one base e, and we're going to divide both sides by 0.097. So if I divide the left-hand side by 0.097, we get this. We get 0.282. I'm going to leave this value. I'm not going to get a decimal on it because it'll be too ugly. And on the right-hand side, we have e to the 0.002675 t. So at this point, we can go ahead and say that the base is isolated. What I want to do is take the natural log of everything. Let's try it again. The natural log of everything on the left and the right. So what this does is it gives us the natural log of all of this on the left here. We have the natural log of 0.282 over 0.097. And this is equal to, because of our inverse property, just 0.002675 t. And so now to solve for t, we just need to divide by our rate here, 0.002675, on both sides, 0.002675. And so we end up with our t here as being equal to this quantity right there. There's our exact value in time at which our populations would be exactly equal. So let's go ahead and work on getting a value then here. We have the ln of 0.282 divided by 0.097. Excuse me, in parenthesis, all that divided by 0.002675. And so what we end up with is 398.95. And this was a time, and so this is in years. And so the thing here is we wanted to answer this question, which was, in which year? Then find the year in which Mexico's population will overtake that of the United States. Well, remember that t equals 0 is representative of the year 2000. And so in order to answer this question, and I don't have a problem typing this one, I've got plenty of space here, we would say that we would have to add 398.95 onto 2000. We would say in the year 2398.95, the population of Mexico will outgrow or overtake the population of the USA. Okay, so going back over some things here really quickly, you guys, I think that it's important that you identify, first of all, that when we look at these population instances, we need to write a model, and that is to say that we need to write a model where we have the initial population and the time. Okay. Once we have that model, though, we can easily compare models, just because if I ask questions like which one's growing at a faster rate, we can just go ahead and compare their rates, or which one had a higher initial amount, we can just look at their initial amounts. Okay. And for this last part here, where we said, you know, where does one outgrow the other, just keep in mind what we're looking for is the time at which our two population models would be equal. And so, in other words, we could just go ahead and set our population models equal to one another, and then work backwards at solving for the time using these algebraic techniques that I shared with you here. Cheers.